Great. We're so excited to kick things off by diving into the topics of temperature and relative humidity corrections with our speaker today. So let me introduce our speaker, Dr. Anika Krause. Hi, Anika.
Hi.
Just a bit of introduction, Anika earned her PhD at the Center for Atmospheric Science at the University of Cambridge. She's an expert in air pollution exposure science, data analysis, and management. In AirGradient, Anika coordinates a global project aimed at testing and improving our monitors. She also ensures that research results and data are openly shared, and she also creates educational materials to make sure that air quality science is more accessible to everyone, just like the webinar that we're having today. A few housekeeping notes before we start. This webinar is designed to be easy to understand, so even if you don't have a scientific background, that's totally okay. We really encourage everyone to actively participate. So please use the chat box to submit all your questions throughout the presentation, and we'll have a dedicated Q&A sessions at the end. Also, we're committed to a respectful learning environment, so please find the brief of conduct in the chat box that outlines our expectation for thoughtful participation. Okay, without further ado, let's give a warm welcome to our speaker today, Dr. Anika Krause. Anika, the stage is yours.
Thank you very much, Johanna. That was a very kind introduction. Thank you. All right, yeah. Since, as Johanna has already told you, and you obviously know, we're talking about the temperature and relative humidity correction of the outdoor open air sensors, so AirGradient open air. Also, as mentioned before, this is meant as an educational webinar, which is also for people who are not air quality scientists. So I should give you the general idea of how to assess the performance of a sensor in general. At the example of temperature sensors here, because temperature is quite an intuitive variable, I would say, to understand in general. But the concepts I'm explaining can also be applied to the performance assessment of other sensors. For example, air pollution sensors like PM sensors or CO2 sensors. Right, so here you can see the overview of my talk. I will give you quite a detailed explanation of the temperature correction, and then I will also go into the correction of the relative humidity sensor, which is kind of analogous. So this will not be it doesn't have to be as detailed anymore, don't worry. So let's start with a problem, especially like the open air monitor from AirGradient is actually quite young. So the last winter was its first winter it experienced. And there we saw, particularly in very cold temperatures, that the temperatures that the AirGradient monitor, the outdoor monitor measures, were actually quite far off from the real values, whereas, you know, at kind of room temperature, it worked fine. So obviously we weren't very happy with this, and we tried to do something about it. First of all, we needed to figure out what actually the reason is. And suspiciously, the reason is because we have this temperature and relative humidity sensor integrated inside the PM module. So probably it has something to do with the sensor casing having a bit of an insulating effect. To confirm this hypothesis, we did a little experiment. So we co-located an open air sensor with a reference instrument. And here you can see we added to the standard monitor, we added another additional temperature sensor, which is directly exposed to the outdoor air. So it kind of dangles out of the monitor. And then we just measured the temperature. So here you can see just a few days of these measurements. And in blue, you can see the kind of standard temperature measurement of our AirGradient monitor. So that is integrated in the PM module. And then in green, you can see the temperature measurements of the external temperature sensor. So it's exactly the same sensor model of the temperature sensor, the same version. It's just the placement which is different. And then in red, you can see the temperature measurement from the reference instrument. And you can see the external temperature sensor works actually really well. It agrees very well with the reference. So it is, the reason is not that the temperature sensor is somehow broken or doesn't work properly. It's just really about the placement of the sensor inside the box. Now you can ask, well, why don't we design it a bit better and design it in a way that the temperature sensor is exposed to the outside air? Well, there's a reason for it, and that's that by integrating this temperature and relative humidity sensor inside the PM module, that allows us in the end actually to get more accurate PM readings, because they are also affected by relative humidity, the PM readings. So the more accurately we know what the relative humidity and potentially also the temperature is at the point of measurement, the better the particulate matter readings will be in the end. And since our monitors are first and foremost to measure air pollution, obviously that kind of gets a priority. But you also don't need to worry, because you can see that although there is quite a big difference between this kind of our standard temperature model and the reference, it still follows the same trends. So the two measurements are actually still really well correlated, which means that there's a good chance that we can correct for this effect really well. To make sure that you can correct a sensor like systematically, first you need to understand whether this error we're seeing is consistent among all monitors. So if we place, let's say, 50 monitors at minus 11 degrees, do they then all measure the same but wrong temperature? Or does every monitor measure like a different temperature? If they all measure the same, that means that if we are able to correct for this error in one monitor, we can just apply the same correction to all of the monitors. So that's important to know if we want to find a correction for all monitors, of course. And this is called the reproducibility analysis. So we're comparing two gradient monitors with each other in the first step. Here you can see how we did that as in an example data set from Ottawa in Canada. We compared two AirGradient monitors over a couple of months, you can see here, and the lines of the temperature measurements are almost the same, like they're really well agreeing with each other. So this is a good sign, a good first start. You can quantify that even a bit better by looking at a scatter plot. So here we're plotting the temperature from one monitor against the temperature from the other. And the closer these points in the scatter plot are to this one-to-one line, the better the agreement is. And and the kind of tighter this line is, the better the linear agreement or the linear correlation is. And that can also be quantified by the coefficient of determination, the R squared value. And ideally, this is 1. So if we look at this data set here, it is really, really close to 1. So the two data sets are highly correlated. Another way to look at it is to look at the actual difference between the two measurements. So if you zoom into this corner here, for example, you see that there's still a bit of a difference between the two measurements. And that can be described with the root mean square error between the two measurements. So it's basically the average difference between the two measurements here. And in this case, the root mean square error is 0.4 degrees. So on average, the difference was 0.4 degrees, which is pretty low. And actually, it's also a sign of a good agreement. So if we now look at our reproducibility analysis of this example in Ottawa, we see it has a really high linearity, and there's just a small difference between the two measurements. So that means the sensors are really highly reproducible. If we can correct one sensor, we can just apply the same correction to the other sensor, and we'll get a good result. But now, if you're very critical, you could say, well, but you only looked at one monitor pair. What if it was just coincidence? And if you look at the next 20 monitors, this looks different. And also we just looked at one location. So what happens if these sensors are in different meteorological conditions, higher temperatures or lower temperatures, for example, do we still have this nice agreement? So basically these results are not yet statistically significant. So let's make them statistically significant. And for this, we're using our data from the co-location project. So we are running a large project, where we have locations all over the planet, where we test our outdoor sensors. And we have a large scientific network, which kindly supports us there by supplying reference measurements, like not only for temperature, but actually even more importantly or interestingly for example, particulate matter measurements or CO2 measurements. And in each of these locations, we usually also have 2 or more air gradient monitors. So we can again look at the reproducibility between the two. So now let's look at more locations, more co-location sites, more locations to see if the reproducibility is everywhere the same. And also look at more than just 2 co-located sensors. So in some of these, we have 6 sensors, for example, up to 6 sensors, I think, co-located or even more. And when I did that, so I did that for a couple of locations, and here you can see the results. So the R-squared value, so the kind of the measure of how linearly correlated, how well agreeing the sensors are, is in all locations pretty much 1. So that is shows that it has really high agreement. And the mean root mean square error, so the average error between 2 monitors is always below 1 degree, and the maximum is basically 0.6 degrees. So this is really good news. That means there's an excellent agreement between our air gradient monitors, and therefore the temperature error can be corrected for. So now we know the problem. We know the reason. We know that it can be corrected for. So we finally can now get to the solution. So how can we correct for it? So the next step is to, instead of comparing the air gradient monitors with each other, compare them with reference instruments. And I did that. I compiled basically a large data set where we compare the raw temperature data from our air gradient monitors with reference data over different locations. So this whole data set here has over 300,000 data points and covers a really large temperature range. It goes up or down to minus 28 degrees, because particularly in the low temperatures, we saw this problem. And if you look at the scatter plot now here again, remember that the further away the dots are from this one-to-one line, the bigger is the error. So here you can clearly see now systematically, the lower the temperatures are, the larger is the temperature error we're measuring. And you can see that it might actually not be like a really straight line. In a first approximation, you could probably say it's like one line for the cold temperatures and then a bit of a different line, like with a different slope for higher temperatures. And this is exactly how we corrected it. So we split the data set into kind of cold temperatures, less than 10 degrees, and warm temperatures, more than 10 degrees. And we performed a linear calibration on each data set individually. So that looks like this. Here we have the cold temperatures. We do perform a linear fit. So basically we're finding a straight line that represents the data points best. And from this fit, we can extract the calibration parameters. So here, this is the scaling factor basically, and this is the intercept. And we did the same for the high temperatures, and we got slightly different calibration parameters. if we now apply these extracted calibration parameters to our raw data set, we get a calibrated data set. And as you can see, this looks much nicer now. The points are much closer to the one-to-one line. Even the R² value has risen a little bit. And most importantly, the average error went down from 2.3 degrees to below 1 degree. So if we go back to our start experiment, so here this again is our experiment with the one temperature sensor dangling out of our monitor. And now that we calibrated the data, you can see that they agree really well with the reference. So that shows that we don't have to have our temperature sensor exposed to the outer air. The calibration, like a simple calibration, can compensate for it, and we can keep it inside the PM module, where it then helps us to get really accurate PM readings. Just a little summary here. So if we look at the average error before and after the calibration, you can see that particularly for cold temperatures, the error improved a lot. So it was about 5 degrees off on average, below 10 degrees, like when you had outside temperatures of 10 degrees and less. And this was now improved to less than 1 degree, which is, I think, an acceptable error for our monitors. So we can say that our temperature error has been successfully corrected. And this correction algorithm, which I showed in the last slide, has already been implemented in the latest AirGradient firmware. If we look at the different locations, just to see how this correction works in different locations. So here you see the raw data first, and you see that especially at the low temperatures, again, the data deviates a lot from the one-to-one line. And if we then correct it, you see that the data looks in all locations closer to the one-to-one line, so the accuracy has improved. But then I noticed this one location here, Van der Bell Park, which looks quite different to all of these other ones, because the width of the points or of the line is much wider than in the others. So let's have a closer look to Van der Bell Park, which is in South Africa. So let's have a little excursion to South Africa. Here I've found the reason. And I can explain it to you by splitting the data set into night data and day data. So here on the left, you can see all the data we measured during the nights. Again, the calibrated temperature compared to the reference temperature, and they lie perfectly on a one-to-one line. The colors show us kind of the weather, so how many clouds were there in the sky. But here at nighttime, of course, the clouds don't seem to have an impact, so no matter what color, they are all lying on this line. If we look at the daytime data, we see that only in the daytime data, we have this kind of smearing of the points. So this larger width of the data points. And we can also see that if there are many clouds, then the points are still closer to the one-to-one line. So that means that these other points here are due to sunlight. And if you look at the picture of where the sensors are deployed, they are like completely in the direct sunlight. There's no sun protection whatsoever, which is good, because it's also good to, if you want to measure air pollution, it's nice to have like 360-degree circulation of air around. So it's a nice placement for sure. But that's why we see, like, when the sun, the quite strong sun in South Africa, hits the sensors during the day, then we get a deviation from the reference instrument, which is probably measuring the temperatures in the shades. So the direct sunlight can have a strong effect on temperature readings. I mean, this is actually not such a big surprise, but I found this data set quite cool, so I just wanted to show it to you. And yeah, that was a temperature correction. So let's just have a quick look also at the relative humidity correction. Here we found a similar issue, that our air gradient sensors was sometimes off from the reference or from the real true value. And in some cases, this was even like off by 15 to 20 percentage points of relative humidity. So again, just like for the temperature, I did a reproducibility analysis to see if this error is consistent, if all the sensors are measuring the same. And again, the R² value, so the measure for the linear correlation, is really close to 1. And the percentage points, like the RMSE, is also relatively small. So we can conclude that, again, we have a high reproducibility also between the RH sensors. So we can systematically correct for this error. I created also a data set where we compare the raw air gradient data with the reference data. Here you can see the scatter plot. And here you can see that the difference is even bigger, actually, from the 1-to-1 line. And you can also see that as in comparison to the temperature data, it's just a straight line this time. So we can just do a very simple linear calibration. So we just extract 2 parameters and calibrate them with these 2. And you can see that now the average error has gone down from 22% to 4%. If we want to go back to our start experiment, so now it's the same sensor setup again, but this time we're looking at relative humidity. And this was in the original data always underestimated. So the air gradient sensors were always showing too little relative humidity compared to the true value. But then when we apply the calibration algorithm, you can see that the relative humidity values agree much better with the reference now. So that is already our solution for the RH deviation. We just use a very simple linear calibration, just one line basically. We also need to notice that through this effect, like through this calibration, we might get values that are higher than 100% of relative humidity, which is physically not possible. So we need to cut these ones out. So yeah, and that is the algorithm, like the correction algorithm, which I'm not too sure. I think we already have also implemented in the firmware, or will do that quite soon. So that's a very quick and simple analysis of the relative humidity. But we will continue to analyze the data while our data set from the co-location project is growing. So potentially there will be a refinement of this correction data. So to summarize our relative humidity and temperature correction, we found that the sensors are generally highly reproducible and accurate. So the errors we found were just due to the placement of the sensors inside the monitor case or inside the PM module. But this could be compensated for by calibrating it. And it worked in all locations and for all temperatures we looked at. And yeah, for temperature, we used a two-step calibration. So we basically parted the temperatures into 2 temperature ranges. For the temperature, we also noticed that the direct sunlight impacted temperature readings. Not very surprisingly, also not much we can do about it because the sensors are actually heating up. But that's something to keep in mind, perhaps. Yes, and also the relative humidity accuracy was improved by our calibration. So what's next then? Currently, we're working like the same performance analysis of the sensors, which I've just explained to you. We can also apply to other sensors. So currently, we're working on the assessment of the PM sensors, the particulate matter sensors. That's a bit more complex than temperature because there the location has certainly an effect, because depending on the location, the particulate matter has different compositions. So it consists of different materials, and that has an impact on on the measurements of the sensor in the end. Also, in our different locations, we have different reference instruments, which needs to be taken into account. And and there are also different other factors that impact the PM measurements, for example, relative humidity. So it's a bit more of a complex analysis here, and it's still ongoing. We also still collecting more data for that to get a really holistic view on that. The CO2 sensor is a relatively new addition to our outdoor monitors. So when we started the collocation project, we mainly looked for reference instruments for PM. So now we also want to look at the performance of the CO2 sensors. So we have already some collocations which also measure outdoor CO2 with reference instruments, but we're also targeting, like we're also setting up more collocation sites where there's also CO2 references. And for the TVOC and the NOx sensors, we've also added them to the outdoor monitors now. And we're kind of still, like, these are quite challenging pollutants to measure, just in general with low-cost monitors. So we're still in the process of like looking at the strengths and limitations of using these sensors in an outdoor environment, and also derive from that the use cases. When does it make sense to measure it, in which kind of questions, and when doesn't it? The use cases for indoor environments are already a bit better defined, I guess. So yeah, so there we are a little bit more at the start of the process, I would say. Yeah, and that's all from me. Thank you for your attention, and I'm happy to answer any questions.
Great. I can see some nice comments in the chat box as well. Thank you so much, Anika, for your interesting presentation and for sharing your knowledge with us. So everyone, let's give Anika a huge virtual round of applause for her insightful presentation. To our attendees, thank you so much for coming. And this is just the first of many AirGradient Education on webinar. So we will bring you more insightful information from science and beyond. So make sure you keep an eye out for our future announcement. You can also find and read the material that we've been discussing in our webinar today in an article format within the link that you can find on the chat box. Ahim will later share it in the chat box so that you can access the link. Thank you so much, everybody. On behalf of the entire AirGradient team, thank you so much for joining us. Have a wonderful rest of the day, everyone.